Understanding electric flux and Gauss's law. Our topic was the relationship with a long uniform line of charge, presented by Toby, Mohammed and Andy. Welcome to our video presentation on electric flux and Gauss's law, focusing on the case of a long uniform line of charge. In this video, we'll dive into the physics concepts behind electric flux and how Gauss's law helps us determine the electric field strength at a certain distance from the charged object.
The electric field's flow through a specific area is measured by electric flux. Electric flux allow us to measure the amount of electric field flowing across a surface around our long uniform line of charge.
To calculate electric flux, we use the formula phi equal to integral of E dA cos theta, where E is the electric field and dA is the negligible area. To calculate the total electric flux for our long uniform line of charge, we integrate over a closed surface enclosing the line.
We select a Gaussian surface that encloses the line of charge to apply Gauss's law. The linear charge density multiplied by the line's length determines the charge that is surrounded by the Gaussian surface. Gauss's law allows us to connect the confined charge and electric field strength to the total electric flux. This allows us to calculate the electric field strength at a point away from the uniform line of charge. This gives us the equation E equals KQ on R squared, where K is the constant, Q is the charge, and R is the distance away from the line.
Due to the electric field directed radially outward and the magnitude of the field is the same across all the pointed on Gaussian surface, and the electric field line are perpendicular to the surface at every point, making the flux calculation easier. You can see in the diagram.
According to Gauss's law, the total charge encircled by a closed surface determines the total electric flux passing through it. The overall electric flux and the charge density along the line can be related by using Gauss's law on our uniform line of charge. Below we have phi of E equals the integral of E dA, which we have already explained, but it also equals Q enclosed over the free space constant.
We are assuming that the symmetrical objects, the electric field is uniform at all points. E can be considered constant across the surface, and the angle theta between E and dA will be the same for all areas.
We chose a sphere as our Gaussian surface due to the spherical symmetry. Electric field emanating from a point charge, we have a symmetrical charge distribution, a uniform charge sphere. Therefore, a spherical Gaussian surface is the most natural choice.
In a spherical symmetry, the electric field makes a constant parallel angle to the surface, making an angle of 0 or 180 degrees. This means that when computing the angle of cos theta, it will equal 1. This simplifies the integrals in Gauss's law, then makes the magnitude relying on the flux through dA.
In this situation, the electric field is uniform across the Gaussian surface. We can treat the electric field E as a constant and therefore take it out of the integral. Simplifying the calculation, we only have the integral of dA multiplied by the constant E, which is the total of surface area of the Gaussian surfaces.
To sum up, Gauss's law and electric flux are useful resources for comprehending how electric fields behave. By applying these concepts to our long uniform line of charge, we can accurately determine the electric field strength at any point in space. Thank you for watching our video presentation. We hope you found it informative and insightful.